Hi, Brent here with Theoretically Practical, and today we're going to be teaching you how to install variable frequency drives, or VFDs, used to control three-phase motors in a simple application like this 1950s era Clousing Model 2520 milling machine. Now, it originally was a single-phase motor on it, but when I got it, it was missing a pulley system that went right here to give you multiple speeds. There would have been like a multi-speed shiv on that, just like there is here. So without that, I kind of skipped it and went to the front with this belt here. So in order to get as much speed variability as I would like out of this machine, I ended up installing a three-phase motor, 3/4 horsepower, and I'll be putting a VFD. So why would you want to put a VFD on a machine? Well, in the case of a lot of older machines, single-phase motors are fairly expensive versus three-phase motors, which you can often get as used takeoffs for next to nothing. This one I got from a friend for free, just because he happened to have it kicking around. So that's also why it's 3/4 horsepower. I'm going to be running it at half horsepower with a half horsepower drive. So to start, I want to clear up some misconceptions about VFDs, and we'll go over here and look at this guy. This is a Automation Direct GS1. As you see, I memorized it, so I had to read it. This is a 120 volt input, 240 volt three-phase output drive. There are a lot of drives from Automation Direct. It's where, for most of your hobbyist guys, that's kind of where I'd suggest to get them. They're very decent quality. They've got a good warranty on them, and they're very simple. And the best part is the manual here is really good at simple explanations of simple installations. So let's talk about what a VFD actually is, what it does, and why you might want one. A variable frequency drive the words are right there. On a AC motor, to vary the RPM, you vary the frequency of the sine wave in the AC signal, which is just how fast the squiggles go up and down. So if you get yourself this beast of an old machine, and a lot of old machines, and especially there's a lot of deals on machines that are three-phase, but you can't just bring them in your shop and hook them up. You can use something called a rotary phase converter or a phase converter. That is a totally different device than a VFD. But in some circumstances, like this milling machine where I've got one motor to control, I'd like to have speed control, I'd like to have an acceleration ramp and a deceleration ramp, and all that built into a nice package, and I have nothing else that I need to control with that three-phase power, then a VFD is a great way to do it, and they're fairly economical. I think this one was like maybe $150, brand spanking new, with a warranty that has run out before I've even turned it on more than once. But that's neither here nor there. Let's talk about, though, the times when a VFD is inappropriate. And these are some real-life examples I've been told about. One is this one will run off a plug-in 120-volt outlet, a 20-amp outlet at that. You can't really run much more than half, maybe 3/4 horsepower from your standard outlet. Actually, only half from your standard 20 amp outlet. If you go up to 30 amps with a 120 volt outlet, you can then go to 3/4 horsepower. I'll be saying a lot of numbers like that, and it's going to get very confusing, but if you go to Automation Direct or any manufacturer of VFDs website, you can look at what the drive horsepower rating is, what the input voltage is, single phase, three phase, 120, 240, 460, whatever, and then the amperage draw on that. So as for practical limitations, I think realistically, if it's under 5 horsepower and you have 220 volt single phase, you can get a drive for a reasonable price that will run it. If it's under 3/4 horsepower, if really under half a horsepower, you can run it off of 120 volt single phase. Now, this is a simplification. There are some tricks that you can do to get out there in the pucker brush and save money and run even bigger machines. But for the average home gamer trying to do themselves, if it's less than 5 horsepower, you can run it on single phase 220. If it's less than half a horsepower, you can run it on single phase 120. And an example of that is I have a friend who has this little scroll saw, and it's a little machine. It's only like 1/4 horsepower, but it didn't come with speed control. It's a very old machine, just has some belts. Well, he can get himself a 1/4 or even a 1/2 horsepower motor, which is bigger than the original, and slap that in there, put one of these on, and now he's got speed control, infinitely variable with a potentiometer. So that's a really nice feature to be able to add on. Now, the 5 horsepower limit isn't to say that if you have, say, a 7.5 horsepower joiner or something like that, you can get a 5 horsepower drive and derate it. And if you're really running it hard, you may eventually find, okay, I do need more power. But a lot of the time you're going to find, you know, the 5 horsepower is plenty, especially if it's a very old machine and you put a newer 5 horsepower inverter duty motor on that. But before you order this, you have to look at the motor. And in this case, this motor is a 3/4 horsepower ball door, and the volts is 208 to 230/460. The amps is 2.1 to 2 or 1. So what that means is if you're running the 200 volt 3-phase, it's 2 to 2.1 amps. And if you're running 460 volts, it's really only about an amp. RPM is 1750. Now, this should also say right here, it says 60 hertz. So what the 1750 RPM means is that at 60 hertz, this will spin at 1750 RPM. And if at 120 hertz, it'll spin at like 3500 RPM. So that's the most important thing you need to read off there. You should also check it out. And this is very difficult to read because the numbering's basically worn off. But, you know, it should be a continuous duty unless you specifically want a non-continuous duty motor for some specific purpose. But if you know enough to do that, you probably aren't going to get much out of this. So once you've got that information, then you can go and look up a drive from virtually any manufacturer. And I would say from my experiences installing a lot of VFDs, I don't see much of a difference in quality between manufacturers. Some are smarter than others. I personally at work, I use control techniques for everything, but that's more because I've got all their little adapters to program the drives. I have all the software. I know how to use it now. Switching to a different drive would just reset that learning period. And control techniques are kind of known for having every feature you want and then a half a dozen more. So, but for simple applications at home, I'd go to Automation Direct. Also because Automation Direct is great at, you just go in the manual, right? Overview, technical specifications, yada yada. Nobody cares. Installation and wiring 2-1. So we'll go there. And you'll be installation and wiring, and you look for it. It talks about clearances and airflow, which is something that's somewhat important. Talks about the drive dimensions, which is great. Talks about circuit protection. So this is a GS1-10P5, 115 volts, 1/2 horsepower, 0.4 kilowatts, 1 input phase, 9 amps of input current, and they suggest a 30 amp time delay fuse or a 30 amp inverse time breaker. So I'm actually running this off of probably a 20 amp breaker that's in the panel. You know, it's not the perfect application, but I really want this to be able to just plug into the wall. So then you go on and just talks about like, oh, okay, so input power with single phase input, you want to put it to L1 and L2 and then the ground to ground, which is great because some drives want it L1 and L3. I'm not sure how much it matters, but it's nice that it's right there and it shows it to you. Then there's the terminal switch. We'll get to the terminal wiring once we get a little further along. So now hopefully I've convinced you that this is the right course of action. At least for this, it is. For you, who knows? But what are you going to need to do it? One thing you're going to need is you're going to want ring terminals. I'm going to show you the proper way to wire up the pecker head, which is the correct term for the junction box on the side of a motor. So we're going to use ring terminals, we're going to use bolts, we're going to use multiple layers of tape. You can see Romex wire going into wire nuts. Now everything about that is just wrong. I wired it up once because I have to play with it. It was a new toy. I mean, what are you going to do? You're going to not play with your new toy? No, you're going to hook it up with whatever crap you have lying around and you're going to be happy with it. But you're going to know that you got to go back and fix that. So never use Romex for this. We'll go over wiring that properly. So as for what you need, I've got some cable clamps, regular electrical type. I'd prefer cable glands, which are like the plastic thing you can see there that tightens around it. They're better for dust, keeping dust out, keeping liquid out, all sorts of things. We'll use them where we can in this, but the wire that I was able to get, the 3-phase wire that I was able to get for the motor is way too big, but otherwise I got to order it and wait and all that stuff. So I made do with what Home Depot had. You're going to want a good sized plug end. You want a 20 amp plug end if you can find one. You're going to want some heavy gauge wire for the cord for it. So I originally tested this using like an extension cord or a cutoff PC cable cord. That's not really going to be acceptable. It's not going to have the ampacity. If you don't know what sort of amperage you're drawing, you look at the manual and then you can cross-reference. I'd absolutely, there we go, recommend picking up a copy of Uglies. It's electrical reference. Mine's 6 years old and I can't believe I could find it, but it's got a lot of good stuff on how to size wire for your application. So pick it up. Mine is all overkill on this. So what I ended up with is I've got my heavy cable for the power to the wall. I've got some of this, you'll see me use this a lot because I end up pulling at work and I end up with these little like 4-foot sections, and rather than throwing it away, I just like to use it up. This is industrial Ethernet cable. This also comes from Automation Direct. It's not the only place I buy stuff from, but it's awfully convenient at times. So we got that. That's gonna go from our control panel to the drive. So this is gonna carry the 3 conductors for the potentiometer because we're not gonna be having this open and exposed. And then there's gonna be 3 other conductors for the forward and reverse switch. So that's what this is for. And this has 8 conductors and I need 6. So it's good quality cable, and then I don't have to just feel bad about throwing away a 5-foot section. And then this is my motor cable. So 1, 2, 3 conductors and ground. You need 4 conductors in that, which is why, and if you go to Home Depot, their selection of 4-conductor cable is terrible. So this is the lightest grade stuff that I could get. I also blame Home Depot when in fact Lowe's was the offender, but they're essentially the same thing to me at this point. So let's go and take a quick look at the control panel that I've set up. All right, this is the control panel, and I ended up mounting it here because this whole head will rotate side to side, and it can also slide forwards and backwards, and the whole top of it can rotate around. So I needed a control panel that wouldn't get in the way of that. I also wanted something that would be easy for me to reach, and right here, this is a great height for me to reach it. The only thing I'd say about it is that the way I mounted it, it's a little bit bouncy, but I can always just keep adding weld to it till it stops. So you've got a 3-position switch here, which is reverse, off, and forward. You got the potentiometer, so you can go slower and faster because we're in Maine and I had to do it. So this is a potentiometer from Automation Direct. We will have the part number in the description, and this is a button from Automation Direct. They take 20mm holes. I absolutely recommend picking up a step drill. So you can use any 10K potentiometer. This is just a 10K pot. These are the absolute least expensive industrial 10K potentiometers by about a factor of 10. If you go for an Allen Bradley 10K potentiometer or a Schneider Electric or any of the other big brands, These are like $350 or $400, and at Automation Direct, they went from 30 to 40. And for the number of times I've said it, you would think I'm getting paid by them, but I'm just trying to lead you guys in the direction of success. That's it. Though if Automation Direct wants to, I'm not going to fight them over it. So this is the control panel. That turquoise wire will go through here. It'll go through the bottom, around here, down the zip tied down the frame so it won't catch on the belt, and into the control box. The control box on the back is where the drive's going to live. Okay, so we're going to be setting up this drive. So when you need to program it, the first thing you do is you hit Program Enter, and then you have this number here. This is for the main menu, I guess you'd call it. And then when you hit Enter on that, then you have the actual parameters. So it would be like menu 9. I don't know what that is on this one. So a lot of times they're sort of separated by groups. So like acceleration and deceleration would be in the same menu, and then this is the parameter itself. So we're going to just reset out of this. So we're going to be starting with example 2 in the book on page 3-9, at least on the version of it that I have, and it's called the variable torque setting. So the application needs, it says the AC drive must control a 208 volt, half horsepower motor, which is exactly what we're doing here. So the parameters should be set at followed. So P0.00 is the nameplate voltage. So we'll hit Program Enter, and we'll go to 0.00, and then you'd enter one more time. And we're going to say this was a 208 to 230 volt motor, so we're going to say it's a 230 volt motor. Okay? Enter. End. Now, the next thing we have to set is the motor nameplate amps. So we're going to hit Program and Enter, and we're going to set that to 2.1. And we're going to hit Program Enter, because that is what we read off of the nameplate earlier. And that actually says for derating motors, basically the range is the drive rated amps times 0.3 to drive rated amps times 1.0. See, you can underdrive the motor nameplate amps, you just can't overdrive them. So we're going to hit Program and Enter on that as well. All right, and then you go to the next step. Motor base frequency, which is P.02. They really do line up these so that's pretty easy for you. So hit Enter, and it's defaulting to 60, and that's going to be your most of the time that'll be what you're using. All right, hit End, and then motor base RPM. So in the case of this, it's 1750, which is the default setting, and that's what you have. You might also have a motor where the base frequency is like 120 or something like that, and the base RPM is 3450. There's all sorts of differences. Just read your nameplate and you'll be fine. So that's 1750, and then P.04, the motor maximum RPM. So 3450, so that's twice the base. So this is a little backwards. On most drives, they don't care about RPM. They just talk about hertz. It's up to you to be responsible about that sort of thing. So I'm letting this go all the way up to 120 hertz. This drive will go up to, I think this one will drive up to 400 hertz maximum, but I don't want to drive it past that high. Even 120 hertz is just so that if I'm slinging small cutters in aluminum, I can get enough RPM out of it to cut it a reasonable way. You don't want to go past 120 hertz, because then your torque absolutely takes a dump, and it really goes bad after 90 hertz. Your torque will be drastically reduced at that point. So those are settings to be aware of. So you hit Enter, End. So we're going to go back up, because the next one we want to hit is 1.00. So we hit Reset, we go to menu 1, we hit Enter. 1.00, we either have ramp to stop or coast to stop. We definitely want ramp to stop, which is the default anyhow. And then 1.01 is acceleration time. I have a 2-second acceleration time. That is from 0 to the base RPM. So this would take 4 seconds to get up to 3,450 and 2 seconds to get up to 1,750. That's perfectly fine. We're going to hit Enter. We're going to hit Reset to clear out of that. And then we're going to want to go to P2.00. So we're going to go to 2, enter, 0, 0. These are the volts hertz settings. There's general purpose, high starting torque, fans and pumps, and custom. And we want 0, which is general purpose. That's fine. You know, we could fiddle around with that if we had to, but we don't want to. So we're going to hit reset. We're going to go to reset again. We're going to go to 3.00. Source of operation command. So there's 0. Operation is determined by digital keypad, which means this alone does it. 1. Operation is determined by external control terminals. Keypad stop is enabled. 2 is the same thing with keypad stop disabled, and 3 and 4 have to do with the RS-485 interface, which is Modbus control. And if you're doing this for your home machine, you're almost certainly not going to touch that. So we do want this to be setting 1. So operation determined by external control terminals. Keypad stop is enabled. I don't see any reason to disable the keypad stop, so that's why it's on that setting. All right, and then we're going to reset again. We're going to go to setting 4, which is source of frequency command. We're going to hit enter. And there's 0, frequencies determined by keypad potentiometer. 1, frequencies determined by keypad up and down. This is the keypad potentiometer. 2, frequency set by 0 to plus 10 volts on AI terminal, which is that terminal there. And that's your plus 10 volts there. So that's the one we're going to use. Then there's, and that means that this switch has to be in the V position, which it is. I is for current. So if you're going to use a 4 to 20 milliamp control signal, which is just a pretty standardized control signal in controls engineering, but we're going to use 0 to 10 volt. So we want 4.00. We're going to hit enter. Right now it's 0 because I was using this for testing, but we're going to want it to be 2, 1, 2. So frequency determined by 0 to 10 volt on AI input. AI switch must be set to V. Okay, enter. Okay, and then we're going to want to go to 6.00, and the default setting is 0 for, this is the electronic thermal overload relay. We're just going to leave it on 0 because that's the default. And user display defined display function is just what this is going to show when it's running, and that's going to be in a box, so we aren't going to care about that. So right now the drive is programmed. We have hooked up to an inappropriately small cable, but that's just for testing. So we're going to actually go ahead and we're going to put this in the box. We're going to wire the box to the motor and the motor to the controls, and that's what we'll be doing next. So what are we going to put our VFD in? You're going to need an enclosure. In this case, I have an enclosure here that houses the VFD and an enclosure up here that's going to house the controls. You don't necessarily have to mount your VFD in an enclosure, but it will greatly increase the lifespan of it and protect it from, in this case, there's going to be all sorts of metal filings and stuff coming around, and there's a fan in most VFDs that would suck in that metal and blow it around on the non-conformal coated electrical stuff inside of it, and that will not last very long. When you're picking a box, it's important to really know your measurements and know that once you've selected it, you will have either selected a box that is too large or too small. There are no other sizes. This is actually the enclosure that I originally intended for everything to fit into, and I was hilariously wrong. So this enclosure I ended up picking up at the dump literally as a guy was getting ready to chuck it in the bin. Now, when you're putting these into T1, T2, and T3, and they'll always be labeled T for the output on drives, you know, what order do you put these in? And does it matter? The answer is no and yes. So put them in whatever order you want from the beginning, but know that if your motor spins the wrong direction, you don't have to change anything else but 2 of these wires. You swap any 2 of these wires, the motor will be running the other direction. You can also wire your forward into your reverse and your reverse into your forward, but I found it's better to just come down here, swap them, and then forward is forward, reverse is reverse. It can help you a lot with troubleshooting later, because trying to get away with doing things the weird way, it will bite you. It will bite you so hard. Okay. All right, one more. There we go. Okay, so that actually doesn't look as terrible as it might otherwise look. Okay. Okay, so we're gonna get this wired up now. The first thing to do is look at on your motor, usually inside the plate. On this motor, it's outside the plate. I'm gonna see if I can get that in a really good spot. You can see it says low voltage and high voltage. These aren't referring to specific voltages. On this motor, it says 208/230 or 208 to 230/460, I think it says. It's real hard to read on this motor. So low voltage is the 208 to 230, high voltage is the 460. It's not always, it could be 120, 220, you know, there's a lot of combinations. So, but it almost always says high voltage and low voltage. And I think all you're doing is wiring the windings of the motor in delta or Y configuration, but it doesn't matter. And actually, just like I said before, interchange any 2 line wires to reverse rotation. And we're going to reverse them if we have to at the VFD rather than up in here, because this is going to be something you don't want to keep tearing apart when we're done with it. So I already know that this is correct, but these wires have numbers on them and they're colored. I've seen a whole bunch of different configurations of how exactly they do this. Sometimes they just have little tags on them. Sometimes they actually have like a nice little bus bar block and you have to move things around. But at the end of the day, it doesn't really matter what you have. So we're going to show the right way to do this. There are other ways that are fine, but this is a way that will always be correct for connecting these wires together. So these wire nuts, for a motor this size, it's probably perfectly fine. But if you're out in industry ever and you want to do it the right way, you put these kind of terminals on it. You take a bolt, you actually bolt them together. This is a nice sturdy mechanical connection. So first you bolt them together tightly. The other nice thing about bolt is it is a spring connection. So as this connection heats and cools, this has room to move in a way. Now I'm going to do it 98% the right way, because you should start with cambric tape. My local hardware store doesn't have cambric tape. It's sold by Scotch. It's like a papery tape that you put on first. That should be your first layer, and you should do 3 layers. So we're going to just pretend this has 3 layers of cambric tape on it. And then you're going to want to use, I've always called it self-vulcanizing tape, but I know that's not the right term. It's this kind of tape. It's rubbery and stretchy, and it sticks to itself. So I usually cut off a predefined length of it. So this stuff's neat because it's got this coating on the other side. I'll get rid of that. And peel this back off. Maybe? No, we're just going to cut that end off. So it's super stretchy tape, but it won't really stick to anything. But if you fold it over like that, it then becomes, well, if you haven't gotten a bunch of dirt in it, it becomes one solid piece of rubber essentially. So it works really well for this kind of thing. So you just take it, get it going. You want to put some stretch into it, or I think. And you just wrap that up. And you'd really like to know that you had about 3 good layers on everything. Obviously, I just cut off way more than I really needed. Just tighten it up. Stretching seems to help it stick to itself. Oh, I know why it's not sticking, because it's not entirely warm out here in the shop. Even though I've been running the heater anytime that I'm not filming. I do have a heater, but I don't have insulation. So if the heater's not running, it pretty quickly drops to ambient. So anyways, you get something like that. Then you grab your electrical tape, and the only reason it's blue today is because I have some Harbor Freight brand black and I have Scotch brand blue. And I don't want to go back up in here. And again, 3 layers. So this would be 3 layers of cambric tape, which I don't have. 3 layers of the self-vulcanizing tape, the self-sticking tape. I don't know. I'll put the proper term for it probably right below where I'm babbling right now. And you just want to get a good 3 layers of that as well. And then that's it. So I'm going to repeat the process. We'll end up with 4 of these because these are the 3 wires that need to be hooked up that way. If it was high voltage, you'd actually have 1, 2, 3, 4, 5, 6 of these things to try to stuff in there. So I guess that's a small favor anyhow. Okay, so now we're going to just wire up the button inputs down here. We're going to start on this end because I think my cable might be almost exactly the right length and not a smidgen longer. So we're going to look at page 2-12, the basic wiring diagram. Hopefully it'll be up on the whole screen instead of what I'm holding in front of it. So you can see for the analog input for the potentiometer, so you got your plus 10 volts, which is there. You got your analog input there, and then your CM, which is your common or your ground. That'll be the middle, the analog input will be the middle of the potentiometer, no worries. And then the forward stop is D1, and the reverse slash stop is D2. And that's from common to D1 will be forward, and then from common to D2 will be reverse. So we're gonna need to run the plus 10, the analog input, the D1, the D2, and the common up to there. So it'll be 5 wires. Forward should be this direction. Forward should spin like that. So we'll put it in forward. And it's backwards. So we're gonna have to switch, and reverse is forward. But we can switch that down at the back of the drive, and we'll do that in just a moment. But let's also check. So we'll go for slower. That's not slower. We'll go for faster. And that's not right either. So for slower and faster, all you have to do is swap 1 and 3. That's it. So we'll switch that. And this was not staged. I'm just an idiot. Or, you know, a lot of these things are like 50-50 shots, and you could probably sit there and figure out which is which, but I'm not going to. Some of you are surely saying by now, well, shouldn't you have turned that off and unplugged it before you did this? And the answer is yes, but I forgot. There we go. Okay. So now, there we go. There's faster, and there's slower. And it'll let you go real slow. Not that you would want to, but I guess it's nice. I don't know. Okay, so we're gonna go around back real quick. We're gonna change 2 of the wires. I'll show you doing that, what I mean by that. And then we'll come back and this will be working perfectly. And we will have completed the VFD installation on this machine, which has been in process for a shamefully long amount of time. Like 3-ish years since I bought everything. Okay, so we want to reverse the direction this runs in. So you've got T1, T2, and T3, and that one's the ground again. You just got to swap any 2 of those. Doesn't matter which 2, just undo one, undo the other one, plug it back in, and plug it back in. You notice I did not do this one live because the other one was 10 volts, and while it could have hurt the drive to short something out, it wouldn't hurt me. In the case of this is 220 volt 3-phase, so it probably wouldn't hurt the drive, but I'm just not going to find out. You know, ignorance can be bliss, and bliss can be good. So we're going to go right back around front. We're going to turn it back on. Everything should work the way we wanted it to. Okay, so we're back around front. We've hopefully fixed everything. I'm going to actually plug it in so that it does something when I flip the switch. If I flip this to, put it medium speed, if I flip this to forward, this should flip the back of my fingers, so you probably won't really see it there. Whereas if it was in reverse, you'd see it like that. So we'll go forward. Perfect. Off. And just to make sure it works the other way, go reverse. You can't see it at all because it's going too fast. Let me do that. Let me really slow it down. Oop, too far. All right, so there's reverse. That's the way I want it. And then there's forward, just the way I want it. And slower is slower, and faster is faster. And don't adjust your picture. This thing is pretty wiggly, but it's perfectly sturdy where it is, and I'm pretty happy with that. So we're going to take a look at the acceleration parameter here and what happens if you set it too aggressively. So we're going to go to 1.01, which is the acceleration time parameter. And remember, this is from 0 to 60 hertz. So if you set your maximum to 120 hertz, then it will double this time to get to top speed. We're going to set it to 1 second, which I don't think will work, and we're going to hit enter, and then we're going to hit reset, reset, and now we're at hertz. And I'm going to turn the motor on. And there you go. It couldn't accelerate that quickly, so it's overloaded, which is what the OL1 means, and if you go into your manual, it'll tell you what that means. That's fine. That's fine. We're going to turn it back to the off position. We're just going to hit reset. We're going to go back into program 1.01, and we're going to crank that up to like 2 seconds. Still pretty fast, pretty aggressive, but now we turn on the motor. Everything's happy. So don't be afraid to play with those settings. You won't really hurt anything by tripping the drive out. That's why it trips, to prevent internal damage. Set your deceleration as fast as you can usually with these machines. And if you need even more deceleration, this drive has R1 and R10. That's where you'd attach what's called a braking resistor. Unless you really need the faster deceleration for some sort of safety reasons, I wouldn't muck about with that. It's pretty simple, but it's almost never necessary in these applications. And usually you can decelerate faster than you can accelerate because you have the whole machine trying to slow itself down. So this concludes the Clousing 2520 VFD installation video, which will probably be called VFDs for you and me, because I think it's funny. And everything went pretty good. You know, I'm using a little bit of a heavier cable than I would have liked to from the motor to the drive, but that doesn't hurt anything. Everything works as intended. It's going to have good functionality for what I need to do, and yeah, you'll probably see this machine again next week because it is missing a handle for to move the quill up and down. Right now I have to do that by hand, and it also should have a small feed wheel so you can do fine adjustments as well by hand. So I'll work on getting some parts together for those. We'll do a little video next week on that. We're going to make our own. For this, we're probably going to buy something, but for this, we're going to make our own in the mill and in my tiny lathe. So, yeah. Thanks for watching. If you've made it this far, like, comment, subscribe. That would be great. Have an awesome week.